Hello, I'm Callahan Monnier, and I'm going to be discussing the Haber-Bosch processes and the current challenges that it faces in our world. So, what is the Haber-Bosch process? It was a process that was invented all the way back in 1913, so it's over 100 years old today, and it amounts to more than 1% of global carbon dioxide emissions. Some sources put it almost at 2%. As a general overview of the Haber-Bosch process, its primary inputs are water, methane, and air. So very accessible reactants, and because this is such an established process, essentially they've worked its way back to the most basic reactants they can get. The initial first step is the reaction of methane and water to form hydrogen. That comes with a carbon monoxide byproduct. The use of water in that process is specifically to prevent the further oxidation of hydrogen so they can control that. It's essentially just an effective way to generate a pure hydrogen stream. They then further evolve the system in order to completely react their methane, which is one of the more expensive inputs, so that they can get a stream that is essentially just nitrogen, hydrogen, and carbon monoxide. Something interesting to note there is that that is an incomplete combustion reaction. If they were trying to go to complete combustion, they would start running into issues where their hydrogen reacts. So that's generally why that's done. And then we have a secondary catalyzation reaction, very similar to what goes on in your car, where they convert carbon monoxide into carbon dioxide. Once that pure nitrogen and pure hydrogen stream has been produced, it's then heated, compressed up to the reaction conditions of the Haber-Bosch process, which are very intense. 450 degrees Celsius, 300 bar, those are some serious reaction conditions. So those heating elements and those compressor arrays are very, very capital intensive. And then, once all of those preconditioning steps are over, we get to the actual Haber-Bosch reaction. We form our ammonia from this nitrogen-hydrogen stream, and we get a very dirty stream full of the reactants and the products out. And because the ammonia is a relatively low boiling point solvent, we're able to capture it with a cooling and refrigeration stream. And then we can separate out the non-condensables, the nitrogen and hydrogen, from it. We get our pure ammonia out, which then goes on to a freight container and gets shipped all over the world. And the nitrogen and hydrogen stream gets recycled to the reactor. So, the current challenges faced by the Haber-Bosch process are the high temperature and high pressure operation requirements, which make it extremely energy intensive to produce. In addition, that also increases the capex requirement for the Haber-Bosch process. So, because you have to build up a significant pressure and you have to use high temperature materials, that increases the cost to build such a system. In addition, in the future outlook of this process, you also have to take into account the carbon dioxide production, which the Haber-Bosch process is extremely responsible for. So going forwards, we're going to have to, make processes more green, more environmentally friendly. So a way we do that is cutting out carbon dioxide production. Any replacement for this process is going to have to solve those problems in order to be competitive against such a long-standing chemical process. 100 years of optimization is some serious chemical engineering and isn't easy to beat. One of the most direct competitors in the current age for the Haber-Bosch process is simply a direct hydrogen introduction. Instead of getting hydrogen from a methane source, instead they use a electrolysis system, or any system really that produces hydrogen, to circumvent the combustion of methane in the process. The issues with this method is that it does not combust the oxygen available in natural air. So in order to get a source of pure nitrogen, we have to introduce another system. So generally that can be done with pressure swing adsorbers or other methods of combustion. You could also consider burning the hydrogen that you're producing to generate pure nitrogen. That's also going to be really energy intensive. So there's a variety of ways to accomplish that. But then you still have the secondary stage of the system, which is a high temperature, high pressure reactor. So you still have this really high barrier to entry in order to get into a system like this. One of the benefits of this method is that it doesn't require a significant engineering challenge to implement. All of these are solved systems with plenty of use at scale. There's not any big hurdles to overcome in that department. Really, the challenge with a system like this is just the fact that it is still extremely energy intensive. The addition of hydrogen generation onto the Haber-Bosch process makes it even more expensive from an energy standpoint. As you can imagine, going from methane, which is one of the cheapest sources of energy on our planet, to electricity, which is still relatively expensive, makes it very difficult to justify economically. So in summary, the direct hydrogen introduction sees an increase in the cost of hydrogen over natural gas, does not fundamentally solve the barriers to entry in what is an incredibly capital-intensive market due to its failure to eliminate the need for a high pressure and temperature reactor at the end of the reactant production system. A novel system introduced by Liu et al. Is a non-thermal plasma route to electrocatalysis. The non-thermal plasma section of this has been explored previously in the literature and is gaining traction. It essentially just produces nitrates, which, if you know anything about cars, the catalytic converter in your car largely deals with converting NOx into nitrogen. It's considered a relatively harmful and dangerous chemical from an emissions standpoint. However, used in a process like this, it's actually quite easy to contain due to its high solubility in water. The direct output of this non-thermal plasma unit in Liu's research is essentially directly put into solution. In scale-up, we would need to look at an absorber column or something that can handle more volume. But this first step is extremely promising because it produces high yields and is significantly more direct than hydrogen production. Because you're essentially taking some of the steps out of the Haber-Bosch process, you're able to produce a significantly lower energy intensity. In this process by Liu, he develops a novel synthesis method for ammonia production. Now, the non-thermal plasma element of this has been explored in previous literature and has gained significant traction in recent times, which is part of the reason why Liu was looking into this. This was the first paper that I was able to find which actually goes from air all the way through to ammonia, purely through electrical methods without an intermediate hydrogen production step. This route is extremely interesting given that it uses two discontinuous electrical systems, the first of which is the non-thermal plasma unit, which essentially just means like arcing electricity. Basically, they're putting lightning in a bottle and frying air with it. They are converting the nitrogen and oxygen in air into NOx, various levels of nitrate oxidation, and then absorbing this into water and then performing a secondary electrochemical reaction in water to turn the NOx into ammonia. Both of these have been explored previously, and they were able to achieve very impressive 92% Faradaic efficiencies in the secondary electrical chemical step. Doing this is essential for any large-scale process. That term Faradaic efficiency is critical to maintain the energy efficiency of the system. If you have a low Faradaic efficiency, you're essentially wasting a lot of energy on side reactions and side products. So the fact that they were able to achieve 92% is promising. It's still actually relatively low for a lot of industrial processes. Typically, we look for 95%, 98%, 99%. So there is still work to be done there, and I think especially the electrodes they're using are extremely well tuned already. So I think there's going to be some challenges there. Once the ammonia is produced in the electrochemical section, that is then bubbled out and then recondensed, similar in the way to the Haber-Bosch process, where the captured elements of the catalytic reactor are cooled and then refrigerated. There would likely need to be a similar step here. I think something of interest is the differences in between this system and an actual pilot system or a full-scale chemical process would be essentially that step. The lab system is able to give a dual purpose to the potassium hydroxide solution they're using to dissolve the nitrate compounds. This would essentially need to become a distillation column, but instead of having simply one chemical being fractionated off, they would need to essentially have the lower half be adsorbing the NOx compounds and the upper half stripping the ammonia compounds. There's going to be some complexities in doing that, but I think it's fairly achievable. It's not going to follow your traditional McCabe-Deely, but you're going to probably be able to still achieve something relatively similar. Ammonia is very easy to remove from water, and nitrates are very sticky in water. So I think that's a reasonably achievable continuous process at scale. Balancing those two, I think, will be very interesting. Something the paper did not touch on a ton was the relative scales of these. There's going to need to be significant exploration in that direction, but it's extremely promising from a process side of things. In this process, the electrolytic catalysis was the rate limiter, not the non-thermal plasma unit, which is promising for further research. The major issues with that, I think, are the already relatively high Faradaic efficiency and the fact that they're using an extremely well-optimized electrode material. They essentially had multiple production steps, where they're using a copper foam and then adsorbing copper oxide. Relatively complex, but because this is a cathode reaction, there's going to be some significant fouling and scaling concerns there. I don't think that's really well addressed in the paper, which makes sense because they're likely working with relatively pure compounds and not seeing any significant contamination. That's going to need to be addressed before any kind of pilot scale research can be done. And that's always really a problem with electrochemical reactors across the board. So either they're going to need to make their electrode solution significantly cheaper to manufacture, or they're going to need to come up with a way to address that concern. Now, an immediate secondary concern is scaling up the plasma unit. That's not the most common reactor we see in chemical engineering. However, it has actually seen use before. So certain wastewater treatment applications have looked at using it actually in a similar capacity for ammonia production, which I think was really interesting, but they were using it in kind of a different way, and there's a lot more fouling concerns there, and it's significantly harder to operate a system like that economically. One of the major concerns with that is going to be the energy intensity, but also the restrictions around the quality of air provided. That's not something that was covered in the paper either. There's going to be filtration requirements and airflow requirements, so that's going to need to be studied before it can go to pilot scale, essentially. I don't expect those to be incredibly restrictive, but you can't have physical particles going through a system like this. Otherwise, you're going to get side reactions, side products, and contamination, and especially for near sea level operation where we're probably expecting to see this. Shipping ammonia is basically always done through large scale shipping, so we're going to need to essentially produce it near where it can be loaded onto a ship. That's something that's common across the world. So we're going to need to know whether or not salt water in the air can impact this unit and what we need to do to remove that. There's a lot of steps that need to be done on the air quality intake for this system still. Something else that I thought was really interesting that the paper didn't really touch on was the fact that oxygen is being produced by the electrochemical side of things. That's kind of a bit of a concern for a scaled system, so that needs an answer. How much oxygen are you producing? I could probably go calculate that from the energy inputs, but I think for the purposes of discussion, just the fact that it's there is worth mentioning. Something that I think is extremely interesting in this that is not mentioned is the potential for that oxygen to actually be used in this process itself. Because we're just taking in straight air from the atmosphere, the ratio of nitrogen to oxygen in the input stream is not controlled. Because we're producing oxygen, there's potential for this to be further tailored. Because the ratio of oxygen is typically higher in NOx compounds, usually it's either NO or NO2. And we essentially have a 4-to-1 ratio of nitrogen to oxygen. That implies that that is very poorly optimized currently. So the potential for oxygen to actually improve the efficiency of that non-thermal plasma unit is something that absolutely needs to be looked at in future research. That's going to make a really big difference in the efficiency, the overall efficiency of this system. Previous research has dedicated non-thermal plasma systems as a technology readiness level 3. This is something that's found in meta-analysis and just my own reading of other papers. I think it was pretty much a clear candidate for readiness level 3. It was just kind of going off of the definitions here. It was beyond a proof of concept for all enabling technologies, like each system had been demonstrated at scale before and had been shown in laboratory research for these particular applications, but they were all individual, right? There was no coherent use of these systems to produce a final product. This research pushes us towards having all technologies in tandem working towards a single goal. I do not think that this system qualifies for technology readiness level 5 because there's still some significant issues, particularly in that dual function of the distillation column as a nitrate absorber and as a ammonia stripper. There's going to be some scale-up challenges there which are not well addressed. As discussed as well, water and air purity requirements for fouling concerns, long-term OpEx requirements are there. And that's, just something that gets solved at pilot scale. Beyond this non-thermal plasma unit, there are other methods. Something that I think still needs significant research and that there is ongoing research in is wastewater recovery of ammonia. I mean, we only really use effectively about 14% of ammonia, and that's on the high end depending on your diet. One of the most well-established methods for wastewater recovery is struvite crystallization, and it's extremely energy efficient. Comparatively, it's about 30% the energy requirement of the Haber-Bosch process, and if you compare it against these new age electrical processes, it's going to be even better because they're generally less energy efficient. The downside of it is it's got to be a relatively concentrated source. You can't just slap this on a river and expect it to work. That being said, I think that's a very significant area of research that needs to be ongoing. Finding new places that we can put it, making these systems able to handle more dirty streams. Essentially, if we could have this on agrarian runoff, that would be a massive source that we could capture. Another significant element of this is the filtration step that I just mentioned. Research is always ongoing in membrane filtration, and new techniques are constantly being developed. There may even be potential for electrical filtration in this specific type of ammonia recovery. In addition, as the non-thermal plasma system we were just discussing grows more mature, that electrochemical ammonia production step will also become more developed. So if that sees a significant increase in its efficiency, there's potential for nitrates in water to be essentially converted into ammonia, and we can skip that non-thermal plasma section or the hydrogen production section of the Haber-Bosch process. And we can just go straight from waste nitrates to ammonia, and we can cut out a large chunk of that, and with that a large amount of the energy requirement. So getting more efficient with our ammonia production is going to be a critical step in reducing the carbon intensity of that industry. And some honorable mentions for other routes for ammonia synthesis. There's a ridiculous quantity of research, and I'm sure there are other competitors in this space. I think one of the most interesting and complex methods is going to be photocatalysis, the use of different wavelengths of light to convert both nitrogen into nitrates and nitrates into ammonia more efficiently. This is kind of similar to like photosynthesis, where plants use light to catalyze the production of glucose. In addition, there's going to be metallocomplexes. This is going to see use in all of these previous methods. I could even argue that the electrode used in the non-thermal plasma unit is a metallocomplex. But the more we know about those systems and how they can affect catalysis, the better we're going to be able to optimize these systems. Biofermentation is also an interesting approach. I think it's one of the more out there ones just because of how energy intensive this process is. The ability of a organic system to produce ammonia is relatively difficult. This does happen in nature, but it's not something that scales well. And something else that I've actually gotten to contribute to myself is the magnetic catalysis space alongside thermal and electrical. These are ongoing fields of research which affect a very wide variety of reactions, not just ammonia production, but if there's a significant breakthrough in one of them, we could see that translate into significantly improved ammonia production as well. All of these are extremely interesting, but generally fall below technology readiness level 3. The reason I brought up the non-thermal plasma unit was because I kind of believe that it was a step beyond that and a step beyond previous research in this field as well. I want to thank you all for watching. This is an incredibly deep dive that I had a lot of fun making on ammonia production and the state of research into it. If you enjoyed this video, leave me a like. I'll be putting out more of this type of content in the future. If you have any comments or essentially recommendations on the direction you'd like to see this channel take, please let me know. Leave a comment down below. Thank you for watching.